Okay, hello everyone, and today our lecture is going to be on network flows. This is one of the most interesting topics in graph theory, and it's something which is, as a problem, something which is quite it's something which is used in real life, but when we get into the intricacies of this topic, it becomes quite interesting, and it's really one of the most fascinating topics in graph theory. So I'll begin and take a lot of time on explaining what the problem exactly is. Because something with network flows is that people don't actually see that what the problem they're trying to solve is. Because network flows isn't something where you're directly told that you're given a max flow graph and you have to find the minimum flow through it. Usually, the problems involving network flows are implicit in nature. So you have to find a reduction from the problem to a network flows question. So, to help with that, let's understand what network flows is. So, network flows, the problem itself is based on what we call a flow network. One second, let me just check that I'm recording. Okay, cool. So, it's based on what we call a flow network. So, a flow network is consisting of a directed weighted graph. So, the graph is directed. Yeah. So the graph is directed and each edge has a weight capacity which we will define as CE, where E stands for the edge, and this value is greater than or equal to 0, so it's non-negative and it's an integer. Okay, just a second. I think this was the color. Yeah, and it's an integer. So for now, this is an assumption that we are making, that all the edges are non-negative integers, and this directed graph has both a source and a sink. We define source as S and sink as T. So just as a quick recap, a source is any vertex which has only out degree in a directed graph. There, its in degree is 0, or the number of directed edges coming into it don't exist. And a sink is the opposite. It has only edges coming into it. So its out degree is 0. Let me just add some more people. Yeah. So this is the input. And our objective is something which I will define in the future. But the basic thing is that you want to push maximum flow from S to T in G. So S is your source and T is your sink. So this kind of makes sense because if you think about what a source and sink represent, it's like the starting and ending point, because the source is from where everything originates and the sink is where everything comes into you at the end. So what we want to do is to push the maximum possible flow from S to T in the graph G. So this word, what is max flow? Max flow is, okay. So first let's define what a flow is. So a flow is a real valued function that, uh, yeah, it is a real valued function that maps each edge of a graph to a positive real number. That is, it's a function from e to the positive real numbers. What this means is, for each edge that you have, it has a correlation with a certain real valued number. So this might sound a bit vague, but as I explain with the help of examples, you will be able to understand what a flow is. So there are quite a few conditions for a flow to be called valid. This is for a valid flow. So most of these definitions are quite intuitive and they can be explained with the help of examples. So if I just think of flow as passing water through tanks and pipes from A to B, such that A only gives water out and B only takes water in, then this is basically, at a very abstract level, what network flows is. So some of the conditions that we have for a valid flow are the following. So for each edge, Fe is less than or equal to Ce. I mean, this seems quite intuitive because Fe is the amount of flow you push through that edge and Ce is its max capacity. So what we are basically saying is, for each edge, you cannot push more flow than the maximum allowed. So if the tank has a 10-liter capacity, you cannot push 11 liters. It's intuitively obvious because that's the maximum capacity. That's how it's defined. Okay. Now, this is quite important, and this is one of the basic and the most important features of the flow network. The sum of Fe, uh, okay, I should have written this a bit better, that's my bad. Yeah, it basically means that, so this is, I'll just give everyone a minute to read the math which is written here, and then I will explain it. Okay, also, are there any doubts so far in what the question is? Like, what are the input conditions, what is the objective, and the few definitions which we've covered so far? If this is a quite, understanding the question itself is quite is quite a challenge in this problem. So if you do have a question, please feel free to unmute or write it in the chat. Okay, I've got a few thumbs up. Everyone else, does what I've explained so far make sense, or should I quickly go over it once again? Okay, I'm getting a lot of thumbs up. Is there anyone who wants me to go over it again? Please feel free to say so. Okay, then I'll move on. Awesome. So what we are saying is that sum of Fe of E out of V. What this means is, I'll explain it diagrammatically. If this is your vertex, and it has all of these edges coming out of it, say E1, E2, E3, and E4, and we say that Fe is the flow. So if this is Fe1, the amount of flow I push out, this is Fe2, Fe3, and Fe4. The sum of this, the sum of the amount of flow going out must equal the sum of the flow coming in. What this means is that you cannot have a reserve or balance that I'm getting 10 rupees, I'll give 8 rupees back. You can't do that. You cannot have a, there has to be a balance. The amount coming in has to go out. And this is what we call conservation of flow. But I am sure most of you would have noticed this, that it's not true for all vertices. There are two vertices for which this won't be true. Does anyone want to answer which they will be? I have written the answer, but maybe someone can try and say it. Yeah, yeah. Source and sink is correct. Yeah, sparse. I'm assuming you wanted to say the same thing.
Yeah, my answer was the same.
Okay, cool. So it is source and sink. And the reason, as you can see, is that a source would never have anything coming into it, and a sink would never have anything coming out of it. So the definition is not going to be valid for these two nodes at all. So we consider v minus s comma t. Okay, so this is small v. In case my handwriting is not evident, this is small v, and capital V is the set of all vertices, and small v is like an indicator which vertex we're talking about. So this is what we call flow conservation, and here I've drawn the same diagram, that the amount which is coming in must be equal to the amount which is going out. Okay, so we spoke that our objective was to push a maximum amount of flow from S to T in G. So we have a notation for this, and we call it Vf, and that is the value of the flow. So value of the flow is the amount of flow which we are pushing from the source. So it's just the sum of the flow values from the source. So we want to maximize Vf. This is what we are trying to do. Is the problem clear? Awesome. I see thumbs up. That's great. Okay. So a quick recap. You have a directed graph with weights, which are the capacities. You have a source and you have a sink. You want to push maximum flow from the source to the sink. And the things you ensure is that you never push more than the capacity it has. And for each vertex, the amount which comes in is the amount which goes out. And the value of the flow is the amount of source pushed from the source. And we want to maximize that. So we just have one assumption that, okay, so there are actually 3 or 4 assumptions, but most of them are covered by definition. So the first assumption is that a source never has an edge coming into it, but that's by definition. The same for a sink. And this was rather key assumption that the capacities are all non-negative integers, but since I've written it in the input, I have not written it here, but it is indeed an assumption. And the assumption that we are making here is that each vertex has at least one edge incident on it, or degree of v is greater than equal to 1 for all v belonging to v. Okay. Okay. So, can someone bound the value of the flow? Can someone give me a bound for Vf? It can be a very trivial bound, but even the trivial bound will lead to something. So, on the basis of this, can someone give me a trivial upper bound for Vf? Max edge weight, sum of all capacities. Yeah, these are both correct. Max edge weight. Yes. What exactly do you mean by, okay, what is Vf? Okay, yeah, sure. So Vf is the value of the flow, and so in your flow network you will have a source, and the source will have edges coming out of it. So the sum of the flows which we push through each of these edges from the source is the value of the flow. Does that make sense? So let me explain it slightly differently. What we get from the user is the flow network with the capacities. We can decide how much flow to put through each edge as long as the flow remains valid. That is the basic crux of the problem. And we, in doing that, want to maximize Vf. Does that make sense? Cool. So, sum of all capacities connected to sink. Exactly. So, this is the bound which I am talking about, but the bounds which were also given are also correct. So Vf is less than equal to the capacity, the sum of the capacities from the source, because that's the maximum amount I will ever be able to push. If I consider all the edges and push as much as I can through each of them, it still cannot be greater than the sum of capacities. And I think this was also mentioned in the answer which was given. Yeah, sum of all capacities connected to the sink, because that's the maximum amount in the end that you will be able to retain. Yeah, max edge weight. Okay, let me think about that for a second. Max edge weight. So what exactly do you mean by max edge weight? I guess you mean max edge capacity. And yeah, that won't be correct, Avigna. I think there is a counter example which can be created for that, because you can break up the amount of flow you push through different edges. But yeah, sum of edges going into the sink is correct. Yeah. So both of these are correct, and thus we can say it's the min of the two. It's, yeah, because one of them can't be greater or you're in trouble. So, yes. Now, our first flow network. So, this is a directed graph. S, A, B, C, D, etc. are all vertices, and the values which I have written in red are the capacities of each edge. So, just to explain how it works, I am going to push flow 8 here, flow 8 here, flow 8 here, and flow 8 here. Okay, does everyone see how this is still till now a valid flow? Because consider A sees 8 flow coming into me from S, 8 flow going out of me to D. Can we have two edges between two different paths? No, we're talking about a simple graph. We're talking about a simple graph. Between every pair of, between vertices, there is one edge. Because, okay, that's an interesting question, and I'm just thinking about it. I think you can do this, right? If you have this, and this has capacity 10 and this has capacity 15, that could be broken to just a 25 capacity edge, right? You could just do that. Yeah, you can just merge. Exactly. Not Jarvis. What you're saying is right. You can just merge. Yeah, you can just merge. But let's avoid that complication for now. But yeah, you can just merge. I'm pretty sure you can merge. Because, yeah, you can merge. It makes sense. Yeah, so coming back to this example, okay, I push 8. Yeah. Okay, now I have a question. Can I push 15 here? Can someone just give me a yes or no answer? Can I push 15 from S to B? Yes? No? Okay, interesting. A lot of varied answers. Okay, so can the people who are saying yes justify their answer? Or Dia or Advik, you can either unmute or write it in the chat. What is your reason for saying yes? Cool, cool, no problem. Yeah, the answer is indeed no. And okay, someone else can answer. Someone who said no, if they want to justify the reason it's no, you can unmute and answer. Yeah, Avigna, go.
Yeah, I think the reason is because there's no path from the source to the sink with weight 15 on all of the edges.
Not quite. What do you mean by that? I didn't get your answer.
I mean, there's not a path from the source to the sink
Mm-hmm.
such that each edge on the path has like a capacity of more than 15.
Okay. I think what your idea is correct, but I don't think you said it in the right way because I think you might have been misled by the 8888. All four values don't have to be the same. What we have to ensure is that flow conservation is maintained. This is what we need to ensure it's a valid flow. And for that, I think you were getting to this, but if you have 15 from S to B, I would have to. Okay, yeah, let me explain. Just 1 second. If you push 15 from S to B, B now has 15 in it, right? It has got 15. So it has to give 15. But if it wanted to give 15, it has to have some edge to which it can move with a capacity of at least 15. But the only edge out of B is B to E. And B to E has a capacity of 1. So the maximum flow I can push from B to E is just 1. So the maximum flow I can receive is 1. Does that
Okay,
make
yeah,
sense?
that makes sense and is a much better explanation.
Yeah.
Yeah.
I think your idea is correct because there does not exist an S to T path, but it was not, I think, accurately said. But I think your idea was basically this. Okay, cool. I'm getting a lot of thumbs up. Awesome. So, yes. Yeah. I push one from here. I push one from here. No problems yet. Uh, how much do I push now? Okay. Now suppose I push 5 from here. So, okay. Now, C has received 5, right? 5 from S. C can go to either F or C can go to B. Now, C has to distribute 5 between the edges from F and B. And you can see that it can like do 5 comma 0, 0 comma 5, anything because the capacities are 22 and 31. But there is a catch. Can I do 5 comma 0? No. It's the same reason as before. Because flow conservation isn't maintained for B. Exactly. No, Advik, you're right. So I can actually not push anything to B because B will then have too much in debt. So I have to push all 5 to F. Now, what F sees is that I have 5 and suppose the one which E got, E had to give it to someone, E has to give it to F. So E goes here. So F has now received 6. So it has to give 6 to T. So we see that VF in this graph is 14. Right? Does that make sense? Is the question, is what we did with this graph making sense to everyone? Note this is not the maximum flow. It might be. I have not checked it. It should be the maximum flow. But this is a flow. It is a valid flow network. And so this explains the problem. We have to choose how much flow to push through the edges such that it's valid and VF is maximum. Right? Okay. So this gives rise to a greedy algorithm from observation. Does anyone have a greedy algorithm from just observing what we did for this graph? Okay, a hint is that Avigna was talking about S to T paths, and if you notice, we've tried to push as much flow as possible. Just combine the two, you get a greedy algorithm. Does anyone have a greedy algorithm to say? Okay, so the greedy algorithm is find an S to T path and push as much flow as you can along the path and just repeat till there is no S to T path. Does it make sense? What we did here was we found an S to T path. We pushed as much flow as possible. Then we found an S to T path. We pushed as much flow as possible. We found an S to T path. We pushed as much flow as possible. We found an S to T path. We pushed as much flow as possible. Did what I just explained, the greedy algorithm, make sense? And do you see why it's greedy? Because you're just trying to maximize the amount of flow you push every single time. Awesome. Oh, is something new in the chat? Okay, cool. Are there any doubts? Okay, now just yeah, that's what I was gonna get to. This does not always produce the correct answer. This is just a greedy algorithm, and it's an intuitive greedy algorithm, but it does not work. So, does anyone want to give a counter example to this? What happens if you choose a suboptimal STT path? Exactly. So, what we did was we chose it in the best possible way because the graph is small. But if you have a humongous graph, you cannot manually choose the best possible path. So, this is the counter example graph that I'm going to give. And does anyone want to say, okay, let me just. Yeah, it's not a correct greedy algorithm. I just said it is a greedy algorithm. And this is actually a nice greedy algorithm because if we see why this went wrong, it will actually give us a very nice intuition into the correct algorithm later on. So, whoops. If I push 20 flow around here, and okay, let me just remember, yeah. And then I push 20 flow here, and then I push 20 flow here. You see that VF is going to be what? 20, right? But instead, if I had gone 20 out here and then just gone 10 here, 10 here, then 10 here, wait, that was not what I meant to do. Yes. And I push 10 here, and I push 20 here, then VF is 30. And this is not opt. Does that make sense? Did the counter example make sense? So the basic thing was that instead of always pushing maximum flow, sometimes you might want to split the amount of flow you send through your edges so that in the long term you have a better situation. And as Avigna said, you might not also find the optimal STT path. So here is where all the magic begins for network flows. Once I pushed 20 from U to V, and then I realized, oh wait, I've messed up. If I had an option to undo 10 flow, isn't that exactly what I want? If I could change this 20 to 10 later on, then I'm getting what I want, right? If I can take out 10 flow from here and then push the 10 back in here, I'm getting exactly what I want. So this concept of undoing flow is what led to the brilliant algorithm given by Ford and Fulkerson. So does everyone intuitively see that this is not a bad greedy algorithm? If we can incorporate the undoing aspect, it's going to work, right? Great. Awesome. So I am going to define the term which is going to basically be the most critical term for network flows, and that is residual graphs. So this is our graph, and now we want to bring the undoing function. So I can't undo in this graph. But, sorry, if I create another graph where I can undo and then maybe link the two together and do something, that might work out. And that's how the something 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 happened, but it all began with the residual graph. So I am going to formally define residual graph. Okay. So for a graph G with vertex set V and edge set E and a flow network F, this is your flow network which we had drawn here. What we define as the residual graph is GF. So GF with V comma EF. So the notation here means that you have the same vertex set because V and V are the same, but the edge set changes, and that's intuitively obvious because when you yeah, even if you're undoing, you don't really change the vertices. There's nothing to change in the vertices. The edges are the ones which change, and when the edges change, by definition, you would have its weight parameter also change, which is what I'll be explaining now. Okay, so this is how you define your uh, residual graph edge set. So if E from U to V is a directed edge in your original graph edge set capital E, we hit two cases and we define two terms, forward edge and backward edge. Now, okay, if CE is greater than FE, what does this mean? If I didn't push max flow, max flow possible, then we call it a forward edge. So if the capacity you didn't push as much as you could have, then you call it a forward edge. And CF of E is the residual capacity. So we had a capacity for G, now we have a residual capacity for GF, and that is CE minus FE. This much makes sense. It's the amount which I still can push, right? Now, backward edges is the interesting one. That is when FE is greater than 0. If I pushed, if I pushed something, you can have cases where FE is 0, like here. From S to V, FE was 0. But if it's greater than 0, what happened? Yeah. If it's greater than 0, then we say that V comma U. This is the undoing term. Instead of having U comma V as an edge, we now say V comma U. V comma U is a backward edge and its residual capacity is FE because that is the amount you can undo. Did I make sense in all of this? This is quite important. So if you did not understand, do stop me and ask me to repeat. Okay, now I'll just ask some questions to ensure that people have understood. Uh, can an edge both be a forward edge and a backward edge? You can raise your hand or write it in the chat. Raising your hand is also fine. Okay. We have got yes and no. So, not Jarvis, can you tell why you think it's yes? Okay. Since someone who said no. Advik or I think it was Dia. Can one of you tell why you think it's no? Yeah, Advik, go on.
So basically, if you want an edge to be, if you want an edge which is forward and then backward, we should create a new one. We shouldn't apply it on the same edge. So basically, if there's a forward edge from U to V, we should create a separate backward edge from V to V.
Okay, I see what you're saying. So, what Advik is pointing out is that here your edge was U to V and here it was V to U. But this is quite, yes, exactly. Exactly. That is the point I was trying to bring out. Exactly. Sparse, would you want to unmute and explain what you were saying?
Is my mic okay? Last time it was a bit weird.
It's all.
So let's say if in the original graph we have both an edge from U to V and one from V to U. In this case, since we reverse both, in the residual graph, we'll have both of them again. So it kind of depends on how you define edges to be distinct, because U to V is a forward edge in the original graph, but since we reversed V to U, it's also a backward edge.
Yeah. So that's exactly right. So it does depend a bit on how you define distinct, but for our purposes, this is just like understanding that um, an edge, as Avigna is saying, it can be a forward edge in one path and a backward edge in another path. And I think, as Not Jarvis was saying, if you send non-zero amount of flow, which is less than the capacity, it's going to satisfy both these conditions. But then you're going to have one is u comma v and one is v comma u. But you can use the backward edge, and then when that flips in the residual graph, you have quote unquote the same edge. So it's a bit confusing, but I hope you understood what forward edge and backward edge is. No, in a directed graph, u to v and v to u is not the same edge. Definitely not. Yeah, u to v and v to u are not the same edge because that's the whole point of being directed. So, yes, this was quite a lot we covered. So, we understood what the problem of network flows is and what residual graphs are. Is there any doubt so far? Like, do you want me to go over an example or cover something again or anything? Okay, I'm just getting a lot of thumbs up. So, awesome. So, okay. Yeah, awesome. I think I will be able to cover proofs. I thought I would not be able to cover proof. Could you give an example of a residual graph? Sure. Okay. So, okay, and let me just find a flow network which works. So, push 3, push 3, push 4. Yeah, maybe I'll push 0 somewhere. I think I'll just push 0 here. Just so that, you understand how it works. Okay, so if this is our flow network, the first thing I will do is copy and paste. The reason you just copy paste is because the edge set is going to be, the vertex set is going to be the exact same. And now, since the vertex set is going to be the same, okay, I think just one sec. I think this is the one I was using. Wait, what? Let's follow exactly what the algorithm says. For each edge E from U to V and E, so okay, S to A. Let's consider S to A. Which case does it fall under? Okay, so CE is greater than FE since 7 is greater than 3. So it's a forward edge. It's a forward edge. And CF of E is going to be 4. Right? Probably this is a bad color. Yeah. Now let's consider A to B. It's also going to be a forward edge with 5. And B to T is going to be with 17. But there are going to be more edges. Are there? Yes, because the flow is greater than 0. Since the flow is greater than 0, you're going to have A to S being equal to 3, B to A being equal to 3, and T to B being equal to 3. I didn't make a mistake, right? I think this is correct. So the backward edges are just basically what you can undo. And now S to C, uh, it has zero flow push. Yeah, so you're gonna have this and this. But no backward edges from C to S or T to C since they don't have non zero flow. Could someone just confirm that I've got the graph right? I think I've got it right. Yeah, I think this is correct. Does this better explain how residual graphs work? Okay, cool. Awesome. So, what the backward edges mainly signify is that you can undo some amount of flow, and the forward edges just mean I can still push that much amount of flow. So, okay, great. I hope that was understandable. Now, I am going to define a function called augment. And yeah, there are a lot of notations and definitions and functions in network flows, but it all boils down to the basic residual graph. So, okay, I have written the entire pseudocode. Just take a look at it, and then you tell me what augment is supposed to do. If you don't get it, it's completely fine. I'll explain it. But if you read this, what do you think augment is supposed to do? Does anyone have any thoughts? You can raise your hand and unmute or write it in the chat. Oh, also, my bad. Equal to 1 means type 1, which means forward edge. My bad. I meant to explain that when I was explaining it. No idea. No problem. Does anyone else have an idea? वीडियो ऑफ चापी दो एक सेकंड ऑफ करो I don't want this function. Yeah, okay. So first I'll define the terms more clearly. I guess at each step we find a path and increase the yeah. That's basically right. That's basically perfect. But if they actually yeah, I think you've got it. Yeah. So I'll just explain what P is. P is an S to T path. F is the current flow. What the bottleneck means is how much can I improve by, and for each edge in the path, if it's a forward edge, then you just follow this definition. You go fe plus equal to b because that's the bottleneck or how much you can improve by, and if it's backward, then u to v was your edge, so v to u is what you would reduce by b because you can undo that much, and then you return f. Does that make sense? I explained it a bit quickly, so if people have not understood, I can explain it again. Yeah, sure, sure. I can take. You guys can take like a minute. Sure. This is quite interesting. But like, if you think about it, it's basically just applying the definition of forward and backward edges on the residual graph and using that on your bottleneck, basically. Ah, that's a good question. Uh, Assume the bottleneck is given to you for now, for each path. If you had something to compute the bottleneck, then if you had something which gives you the bottleneck for each path, do you agree that this works? Yeah, I should have mentioned that. My bad. My bad. If you have something which gives you the bottleneck, does this make sense? Sure. So, what the algo means is that, just a second, I'll get back to that. Do also. Uh, what exactly do you mean? You as input you are given the capacities. Yeah, fe, yeah. So in the beginning, okay, I get your question. Okay, so if we go here, in the beginning all the flows which you have pushed are zero, but then once you start beginning your algorithm, you decide how much flow is pushed on each edge in each step. In the beginning it's zero. Yeah, that was your question, and the answer is yes. Okay. So what the algorithm means is that if you have something which can compute the bottleneck for a path, then for each edge in the path, I can check if it's forward or backward, and then depending on that, I can use the definition to figure out what the flow is going to be for that edge, and from that I can decide like the flow of the graph. Does that make sense? Okay. So I'm trying to understand your question. Give me a second. Yeah, exactly. It's an undoing option. Yeah. This isn't VF. This is like the for as I think yeah, the bottleneck is basically how do I explain bottleneck? So bottleneck is basically for that path. How can I improve it? Basically for like the edges. Yeah, no problem. By the way, for the internet. Look, not Jarvis. It's an option. Like the whole point of the entire residual graph system is that given the backward edges, you have an ability to revert. You can pull back flow, right? Also, when I get to the Ford Fulkerson's algorithm, this hopefully will get clear. Oh, I showed the lemma. Oops. Yes, exactly. If it is going to give you something better, we can revert. Now, this was a bit. The augment thing does confuse. It confused me as well when I first did this. So, does it make sense? In theory, it is saying that on each step, can I improve? Basically, on each step, how can I? Okay, can I please? Just the augment thing, or like more than that also? Like, it's okay if you need more. Just augment. Okay. So, what augment does is that it takes a path from S to T. Okay. Then for each edge, it tries. Okay. For each edge, it checks if it's forward or backward. Depending on whether it's forward or backward, it uses the bottleneck to assign values to the residual graph and the graph and the flow network, basically. Instead of graph, we can use the term flow network. Does that make sense? Awesome. Okay, cool. I am glad that made sense. So I am going to give a lemma now. If you can get some flow f dash from augment, it's going to be valid. Does anyone want to take a shot at proving this? Or do I have the proof? Uh, yeah, okay. I think the proof of this is. Okay. I'm going to leave the proof of this as an exercise. And it's quite interesting to try and prove this. It shows like if you understand augment properly, you will be able to prove this. But because augment is a bit confusing in itself, I really don't want to go into the proof right now. Yeah. Is that okay? I can give it as a note. Like, I have the proof. I can just send a screenshot or type it out. Just assume the lemma for now. That if you do augment, you're going to get a valid flow. And going back to the definition, valid just means that FE is less than equal to CE and sum in equals sum out. Okay. So after all of this, I am going to explain Ford Fulkerson's algorithm. Yay. Okay. Now, yeah, I'm going to show the algorithm so you can all read it and understand it and then explain it. So take like 2-3 minutes, try and understand what this algorithm is trying to say. If you have any doubts in definitions, just tell me. I think everything here has been defined. Fe is the flow of edge. Path. Yeah, I think everything has been defined. But if you do have a doubt, just yeah. Ah, okay. This means there exists. Whoops. It means there's like it's like while number of S to T path. No, I mean on the first line below the title. Oh, this. Oh, it's flow of edge. Like Fe, what we defined like here. The flow you're pushing on the edge. Yeah. Oh, it's an F. Yeah, it's an F. My bad. Yeah, it's an F. Yeah. I will write that again. Yeah, it's an F. So initially it's 0. Yeah. Okay. So continue reading it. Also, one thing I just like to say is this is like a one-time statement. Every single time you don't do every single time you don't set g after g because that would just be pointless. Also, this is a crude way of writing it, but we're just equating the vertex sets. Okay. It's like abusive notation, but yeah, I am abusing notation. GF is the residual graph. This thing. GF is the residual graph. This thing. Does the algorithm make sense? Like intuitively, does it make sense? Okay, I think it will be nice if someone is able to summarize Ford Fulkerson's algorithm um, by saying it. So that will probably help you understand intuitively how it works. Does anyone want to say it? Like what they think Ford Fulkerson's algorithm does? Yeah, Vigna, go on.
Yeah, so basically it's like you have this residual graph and you keep searching for a path of an STD path with in the graph, and as long as it exists, you augment the path and you update the values in the residual graph, and you keep repeating. Wait, just a second. Should the while line find an STD path from G in G or in GF?
Uh, okay, 1 second. That's a good question, and I have to think about that for a second.
Because there might be like a case where you have like a path, but the path is like you can't push any flow on the path.
Okay, just give me a second. That's a good question. I myself am a bit confused. Give me a second. No, no. It will be while there exists an SST path in G, because what we are doing is that we're saying, okay, if we go back to the example, we are trying to cover every possible S to T path. So here it would be S to A to B to T. Here it would be S to T, S to C, and S to T. There are only two S to T paths. So this would iterate only twice. While in the residual graph, it does not remove uh, S to T paths, right? You can't remove an S to T path. You can just visit it once.
Okay, so can you go back to the example where the optimal flow was not chosen in the first case?
Sure.
Yeah, this example, right. So in this case, if you just consider this graph,
Mm-hmm.
like the STD paths you have are like S to W to V to T, right? You also have S to W to T,
Yeah.
and you have S to V to T.
No, I think these are the only. Okay, yeah, you have three, right? Yeah. Mm-hmm.
Yeah, so when you are doing like the undo operation, isn't one of the paths going from S to V to W to T?
Yeah, yeah, yeah. It is. It is in the residual graph. Okay. Do you want me to draw? Okay. See. Okay.
And the
Yeah.
thing is,
I don't
that
get your
path isn't.
question though. This is not an STT path, right?
It is not indeed, yeah, but that is the path we are considering.
I don't get your question. What?
Like like if we ran the algorithm on just G, it wouldn't find this path and wouldn't like by that logic would not be able to make this improvement.
Uh,
Do you understand my question?
yeah, yeah. I get your question, and it seems to make sense to me. Uh, you know what? Just give me a second. I actually want to check this. I don't want to say something wrong. Just give me a second.
Yeah, sure.
I'm literally just gonna Google the algorithm. I don't want to be making a mistake. Because I am confused, and that's not a good thing.
Yeah, no, no worries.
Yeah, because your thing makes sense to me, but like the way I remember it is like you check it in G. So I could have done it wrong. You are right. Augmenting path. You are absolutely right. Okay, my bad. You are right. That is a very good catch. And I'm sorry. Okay, one second. My iPad is a bit slow. Yeah. Sorry. Sorry about that. I got a bit confused myself. But yeah, yeah. I think Avigna explained it very nicely with this example. Did everyone understand it? Sorry about that. I got a bit confused myself. Okay, cool. So yeah, does Ford Fulkerson's algorithm make sense to everyone? Okay, cool. So I'll just give a rather obvious lemma. At any time, the flows and residual capacities, Ford Fulkerson's in an example. Uh, okay. Okay, I should have had a pre-ready example because making an example will, like, actually, can we do it in this? Like, I think we can do it here, right? This is not a bad graph to do that. Or actually, you can intuitively explain, I think. Avigna, would you want to intuitively explain why it's like this path in the residual graph by Ford Fulkerson's?
So the thing is, that is the path you have to take to undo the flow.
Exactly.
In some cases, to undo the flow, you will need to take a back edge.
Yeah.
So
So
that's the reason I thought it has to be in the residual graph and
yeah,
not.
that makes sense. I think she was asking for an example of what Ford Fulkerson does on a graph. So do you want to just explain it for this?
Um, I mean, yeah. So pretty much, the first thing you do is you push a path from S to W to T, right?
Yeah,
Is
it's
that what
U,
you
but
did?
yeah. So Ford Fulkerson will first go S to U to T, and it'll do the
Like you,
augmentation
my
for that.
bad.
Yeah, no problem. Yeah, then go on. Okay,
Okay. Could you draw like the flow, the push flow?
sure. Okay. So I don't think that's actually required, because what you can just say is that look at this exact same example. You can go S to U to T, then you can go S to U to V to T, and you can go S to V to T. But when you would have formed your residual graph, you would have seen that like there's 10 or 30, in both cases you have either 20 or 30 flow which is pushed here. So this guy will form a back edge here, because it's going to have some flow greater than 0. And that back edge is actually going to give us another S to T path, which is going to be S to V to U to T. And when we find the flow for that, it's going to be optimal. So that's what Ford Fulkerson does. And did I explain it correctly? Is that you, that's what you were trying to say, right?
Yeah, that sounds right to me.
Okay. DR, did that make sense? I can send like a proper example with like many nodes. That's just going to be like kind of disastrous to try and implement. It will always be optimal. Yes, Ford Fulkerson's algorithm is always optimal, and I'll be proving that. Or maybe, I'm not sure if I'm proving that. The proof is quite involved. I can go over parts of the proof, but maybe just a sketch, and I'll give the proof as like reading, because if I try to go over the proof, it'll take at least another hour. It's quite an involved proof. At least for me, it's quite involved to, you know, go over the proof. But yes, it is always optimal. Ford Fulkerson's algorithm is always optimal. So the first lemma is that at any time, which means after some k iterations, the flows and residual capacities are integers. I think this is quite trivial to prove, and it's just induction on the number of iterations. Like your base case is 1, then, oh sorry, 0 and 1, you can just do both. And then induction hypothesis is that it works for k, and then induction step would be k plus 1. You can also do strong induction. There are many ways to do this with induction, but induction on the number of iterations just kills the proof. I hope everyone understood that. The lemma. The lemma is quite intuitive. This is the next lemma, that okay, if I did augment and I got Vf dash, and if Vf was my original flow and B was my bottleneck, then Vf dash is going to be greater than Vf, which basically is saying that bottleneck is positive. And the proof of this is quite nice. So you see, like the first edge, or the one from the source, have its tail on the source, or that's its origin point, and its head at the vertex where it's going away from. If you think of this edge in the residual graph, it will be a forward edge if you don't push full amount of flow. And then since it's forward edge, you can use augment plus bottleneck, and there's a nice proof for this. This is the sketch. This is the main part of the proof. You consider this. So I'm leaving a lot of the lemmas proofs as like exercises, because they're quite fun, because they explain um, the algorithms and the functions very nicely. But if you like don't get one of the lemmas proofs, just you can message and I have the proofs for them, so I can give those proofs or explain them, whichever. So I think there's this lemma. This lemma is trivial to prove, but this lemma is quite nice. Okay, f dash is the value I got when I augmented. And I think there's one more lemma. I think this was another lemma which you have to prove. And I think if you prove this, then the next one becomes quite easy to prove. So they're like in sequence. Okay, so we have done Ford Fulkerson's algorithm. Whenever we do an algorithm, what's the immediate thing we think of? Proof of correctness, runtime, right? So for now, just believe me, the proof of correctness, it exists. It is true. So let's do runtime. Okay. So a new notation. Let's see capital C be the sum of capacities out of the source. So till now we had Vf, which was the sum of Fe for E out of S. Now we have capital C, which is the sum of the capacities instead of the flow. Okay, now another lemma. I have left a lot of lemmas to be proved, and some of these lemmas are like super important. So you should definitely try to prove these lemmas, but you don't need them for like just comparative programming. If you just know these lemmas, if you just know Ford Fulkerson's, to be honest, it's enough. But I like the theory, and yeah. So the max number of iterations for Ford Fulkerson is capital C, and that gives us that the runtime is O of n plus m times C, because finding an S to T path with BFS would be n plus m. Augmenting is O of n. Again, that depends on how you find bottleneck, but you can just say it's O of n because it is. And then this is O of 1. And then since this is just updating adjacency list, it's going to be O of degree times m. So overall, it's going to be O of n plus m times C. This was a bit of a hand wavy explanation of the runtime, but this is the basic runtime. This intuitively it makes sense. If the max iterations were C, why it would be n plus m times C. Okay. Yeah. Yeah. So the min cut max flow theorem states that Ford Fulkerson's algorithm. Could you explain how you find the bottleneck? Uh, I think I have it written down. If I don't have it written down, I have it in the notes, which is on the laptop. So as soon as the lecture is over, I will go over that immediately and tell it to you. I don't have it on the top of my mind because I've not done the implementation of Ford Fulkerson's after that Division 2 problem. But I have it on like saved on the laptop, so I can tell you as soon as the theory part is over. Yeah. So yeah, uh, this is called the min cut max flow theorem. And does everyone here know what a cut is? A cut is basically a partition. Just give me a second. I'll put this in charging while I'm talking, so it just recharges for some time. A cut is basically a partition. Any cut partitions a set of vertices into two sets. And what the cut here does is that S, which is the source, is in one partition and the sink is in another source, is in another partition or set. What you want to do is minimize some parameter. So here you want to minimize the number of like, I don't know how to say this. Okay, the min cut gives you the max flow. If you are able to find the min cut, you get the max flow. Does that make sense? Okay, cool. So how do we find the min cut? I'm talking a lot about min cut, but okay. So this is a question which you guys might want to answer right now. So how do we find the min cut? Hint: use what we just learned. Okay, min cut is a partition of the vertex set into A and B such that A has source, B has sink, and you get max flow. Okay, so I'll give the first step. Do Ford Fulkerson's algorithm. Do you want to find the edges in the min cut or just the size? Okay. Uh, hmm. So what I was trying to say is, can you give me the partition, like um, which vertices are in set A and which are in B? You don't need the edges. Just yeah. So just the size. Yeah, you could say the size. And okay, uh, I'm not sure. Like, okay, I don't think I'm explaining min cut the right way. Uh, I'm trying to think of another way to explain min cut. Just give me a second. Uh, by the way, just from like the way you're answering sparse, do you know how to define min cut in a better way? Because I don't think I'm defining it in a way which is understandable. Like I know what it is, I'm not able to define it properly. So, do you like, because from the way you're answering, I just feel like you know this. So, would you be able to define min cut, or I'll just take another shot at it otherwise? Yeah, it is hard to put it into words. Okay, I'm just trying to think how I can explain it. Sorry, it's just like min cut max flows always seem like a very natural thing. So I don't know how to define it. Just give me a second. I'm trying to think. So you partition your vertex set into A and B, where A and B are sets having vertices such that the source is in one and the sink is in the other, such that the maximum weight of flow which you push from the source, yeah, that's the definition. So the disconnect part is what I was trying to say through partition, and yeah, you want to minimize that parameter. Okay, if the Wikipedia definition makes more sense, yeah, it does make more sense because it's Wikipedia. So, okay, I'm going to say the definition aloud. The smallest total weight of the edges, which removed, which if removed disconnects the source from the sink, which means, in the words I was saying, you want to find that partition or that cut such that it is minimized and source and sink are in disjoint sets. Does that make sense? And a corollary is that when you do this min cut, you get a max flow. Yeah. Sorry for the bad way of explaining it. It just, I realized it seemed intuitive to me, but when I tried to explain it, I was not able to explain properly. So, thanks for the definition. It helped me as well. So, yeah, does someone want to take a shot at how finding the min cut now? The first step is to run Ford Fulkersons. That's a hint, I guess. And think, when you run Ford Fulkersons, in the end you get a residual graph. Can you do something with it? Yes, but after you run Ford Fulkerson, at the end of Ford Fulkerson, when the yeah, that's a very good explanation. Yes. So if there exists an SST path, then it cannot be disconnected. As long as it's disconnected, as long as flow exists, it's not disconnected. But when does Ford Fulkerson end? When does it terminate? When there is no S to T path. So when there is no S to T path, you can partition, right? Does that make sense? Yeah. So this is what you actually do. You do BFS from the source. Okay, 1 second. S to A. Uh, so a valid cut just means that you have two sets and S and T are in different sets. So if you cut, yeah, so you're saying your set capital A is S and A and your capital B is B and T, right? Those are your two sets. So then, yeah, this would be a valid cut. Yeah, yeah, it's a valid cut. Yeah. If I understood your graph correctly, yes, it's a valid cut. So, yeah. You run BFS and then would a partition into more than. Hmm. It's a nice question. I have no idea. I have not thought of that. In terms of definition, we define it as two sets. You divide it into two sets. One contains S, one contains T. You can probably extend the definition, but I've never thought of that. So in terms of definition, it's just two sets. So yeah, your first set would be everything reachable from S, and the rest is B. Again, leaving the proof of this as an exercise. I have left a lot of proofs as exercise, but I don't want to go into all of these proofs because some of them are quite detail oriented and require like loads of lemmas, especially like very very small lemmas which build up to the proof. So I feel like it might be too much if like you're doing flows for the first time, because I did not understand it at all when I was doing flows for the first time. So we could do one of two things. You can try out the proofs and then I can give hints, or we can just do another lecture. I'm okay both ways. But I definitely feel having all the proofs right now would. Yeah, but if the source and sink are in distinct groups, you have a partition, right? You have. Okay, the stylus isn't charging, it's charged. Yeah. You have some cut like this, such that all the vertices here and all the vertices here are distinct. This has S, this has T, this is your min cut. And the flow from S to T here is your max flow. That's what min cut max flow theorem states. Yeah. Now I have a statement. Can you tell me if this is true or false? When the capacities are integers, the max flow is always integral. Okay, now we are going to relax this definition. That flow of each edge, this thing, is going to be relaxed. Just for this one question. It doesn't have to be an integer. Okay. We're going to relax that. Yeah. So then is the max flow always integral? Yeah, exactly. For this case, you can push a non-integer flow. For everything so far, no, we are assuming integer. Yeah. Yeah. Is the yep? I didn't get what the true and yes is. Ah, okay. No, 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 no. Can you justify why you think it's true? Because I'm saying the answer is false. And the reason is a trick of words. If my statement was when the capacities are integral, there exists a max flow that is always integral,